All right, everyone, welcome. If you're gearing up for a test on thermodynamics, you have landed in exactly the right place. This explainer is built from the ground up to give you a fast, effective review of all the core concepts you absolutely have to know. Okay, let's dive right in by looking at the name itself, thermodynamics. It comes from two Greek words, therme, which means heat, and dynamis, which means force. So right from the get-go, the name itself tells you what we're studying, the forces and changes related to heat and energy. So here's our game plan. We're going to build this up step by step, kind of like a pyramid. We'll start with the basics, the thermodynamic universe, and then figure out how to describe a system's state. After that, we'll hit the first law, which is all about energy accounting. Then we'll explore different thermodynamic processes, move on to the big one, the second law, and wrap it all up with the Carnot Engine, the ultimate theoretical limit.
First things first, we've got to define our playing field. In thermodynamics, you have to be super precise about what you're looking at, and just as importantly, what you're not looking at. It's all about setting the stage correctly.
It's actually a pretty simple but really powerful framework. You've got the system, that's just whatever little piece of the universe we're interested in. Then you have the surroundings, which is, literally everything else. And the line between them? That's the boundary. Now, this can be a real physical thing, like the walls of a beaker, or it can just be an imaginary line we draw for our analysis.
Now, this is where it gets interesting. We classify these systems based on what they're allowed to trade across that boundary. An open system, like an open pot of boiling water, can swap both mass, which is the steam, and energy, which is the heat. A closed system, like a sealed bottle, can't lose any mass, but it can still exchange energy. And then you have the isolated system, our perfect thermos, which exchanges absolutely nothing. Nailing this difference is going to be critical for your quiz. Okay, so we've got our system defined. Now, how do we describe what condition it's in at any specific moment? You can kind of think of it like checking a patient's vital signs or looking at a car's dashboard.
We do this using what we call state variables. These are the measurable properties that tell us everything we need to know. The big three that you'll see all the time are pressure, P, volume, V, and temperature, T. If you know these, you know the state of the system.
And these variables fall into two main categories. On one side, you have intensive properties. These don't care about how much stuff you have. For example, the temperature of a drop of water can be the same as the temperature of an entire lake. On the other side are extensive properties, and these guys do depend on the amount of matter. Mass and volume are the obvious ones. The more stuff you have, the bigger their value.
All right, we've got the vocabulary down. Now let's jump into the first major rule of the game. You'll often hear it summed up with this phrase: you can't win, you can only break even.
The first law is all about answering this one really crucial question. We've all heard that energy is conserved, right? But thermodynamics forces us to get specific and account for every little bit of it as it moves around. And at its heart, that's all the first law is. It's just a restatement of one of the most fundamental rules in all of physics. You can't make energy out of nothing, and you can't make it disappear. All you can do is change its form, from chemical to mechanical, from electrical to thermal, and so on.
So, this all comes down to a simple equation that works like an energy balance sheet. The heat you add to the system, delta Q, has to go somewhere. Part of it, delta U, goes into changing the system's internal energy, basically making its atoms and molecules jiggle around faster. The rest of it, delta W, is used when the system does work on its surroundings, like a gas expanding and pushing up on a piston. It all has to add up. So a system can change from one state to another, right? But here's the kicker. The specific path it takes to get there really matters. These different paths are what we call thermodynamic processes. And the best way to see this is with a PV diagram. This thing is an absolutely essential tool. It's basically a map that lets us watch how a system's pressure and volume change as it goes on its journey. The route it takes from state A to state B can look totally different, and that path determines things like how much work is done. Now for your test, you've got to know these four main types of processes. They're each defined by what's being held constant. Isobaric means constant pressure. Isochoric means constant volume. Think of heating gas in a sealed rigid box. Isothermal means constant temperature. And then there's adiabatic, where no heat is allowed in or out. This happens when a process occurs so fast that there's literally no time for heat to be exchanged, like the compression stroke in an engine. Okay, on to the second great law. If the first law's motto is "you can't win," this one is often summarized as "you can't even break even." This law introduces a fundamental limit to everything and basically tells us which way time flows.
So, the first law tells us energy is conserved, which sounds great. But the second law gets real and explains why some things in life are a one-way street. Why does your hot cup of coffee always get cold? Why can't we build an engine that's perfectly efficient? This law has the answers.
What this law really does is dictate the natural direction of things. It's the universe's rulebook. It explains why heat always flows from a hot object to a cold one, and never, ever the other way around spontaneously. It's the law of nature.
And the implications here are huge. First, as we said, heat doesn't flow from cold to hot on its own. Second, and this is a big deal for engineering, it is impossible to turn all the heat you get from a source into useful work. Some of it will always be wasted. And third, on a cosmic scale, every single energy transfer increases the total disorder, or entropy, of the universe.
And all of this brings us to the payoff, applying these laws to engines. So if perfect 100% efficiency is impossible, then what's the best we can possibly do? This is where the brilliant idea of the Carnot engine comes into play. It's the theoretical perfect score. So let's break down how a heat engine works. At its core, it's a device that takes heat from a hot source, uses some of that energy to do work, like turning a turbine, and then, because the second law says it has to, it rejects the rest of that energy as waste heat to a cold place or a sink.
Okay, so the Carnot engine isn't a real machine you can go out and buy. It's a thought experiment. It's a perfect, idealized engine that represents the absolute maximum possible efficiency that any engine could ever have when operating between two specific temperatures. It's the theoretical speed limit.
And here it is. This simple formula tells you that ultimate speed limit. The max efficiency is 1 minus the temperature of the cold sink, T2, divided by the temperature of the hot source, T1. Oh, and this is absolutely critical. Those temperatures have to be in Kelvin. No engine, no matter how clever the design, can ever beat this number. It's a hard limit set by the laws of physics themselves.
So this leaves us with one last kind of mind-bending question. The second law tells us that the total disorder, the entropy of the universe, is always increasing. So if every single process, every star that burns, every engine that runs, is pushing the universe toward more chaos, what does that mean for the end of the story? What is the ultimate fate of the universe? It's a question that takes these simple principles and scales them up to the entire cosmos.